All right, now that we've been introduced to the central limit theorem in the previous section, and we know that sampling distributions have their own distribution, and under certain conditions, they follow a normal distribution, okay? And why is that important? Well, because a normal distribution is a very well understood distribution, has a lot of nice properties, okay? Now we're going to talk about a different sampling distribution, okay? And this is something we haven't even mentioned throughout the course yet, but we are going to use this for the remaining portion of this course, okay? So we're going to describe the sampling distribution of a thing called the sample proportion. So in the last section we talked about the sample mean. Now we're going to talk about something called the sample proportion. Okay, so what is a proportion? Well, you can think of it as like a percentage, okay? Now suppose a random sample of size n is obtained from a population in which each individual has or does not have a certain characteristic. Then the sample proportion denoted by p hat is given by this thing which we call p hat. Okay, we actually call that p hat because it has a hat on it. Okay, that's x over n. Okay, so this is your sample size, and x represents, well, it says the number of individuals from the sample that have a certain characteristic that we're looking for. So for example, if I was interested in figuring out the proportion of left-handed individuals, right? So let's say I go ahead and I have my class of 30 students, and that would be my sample size, and x would be just the number of left-handed individuals, okay? So you can think of this as like a percentage of those who are left-handed, okay? One thing to note here is that your x can never be greater than your n, right? Because it's those individuals from the sample that have that characteristic. So the sample proportion is called p hat, and the population proportion is just called p. Okay, so this kind of goes away from the convention that we use Greek letters for population parameters, right? In this case, we just have the letter p. And then for the sample statistic, we're using p hat. So p and then p hat. So again, you want to think of this as p is like the true value. The population proportion is the true value. And if you don't have access to all the population data, well, the best we can do is take a sample, do the exact same calculation, x over n, but we call that p hat. Okay, so this is an estimate of the population proportion. All right, so for example, a poll asked 1,140 registered voters nationwide whether they were concerned about climate change. 752 answered concern about climate change. Obtain a point estimate. Okay, a point estimate is just a single value that estimates a parameter for a proportion of registered voters nationwide who are concerned with climate change. So the point estimate for a proportion is just the sample proportion, which is just x over n. In our case, our sample size was 1,140 voters, and 752 of them were concerned about climate change. And if we were to divide those two numbers, that would round to about 0.6596 if we're doing 4 decimal places. Okay, so again, a sample proportion is a calculation done on a sample, right? Now, from sample to sample, if you actually asked another 1,140 registered voters, maybe a different group of 1,100 registered voters, do you expect there to be exactly 752 to be concerned about climate change? Well, I don't expect exactly to be that. It should vary from sample to sample what that count is, okay? It might be 760, it might be 730, it might be 745. It might be close to the 752, but not necessarily exactly 752. So if sample proportions vary from sample to sample, therefore the sample proportion has its own distribution, okay, which is illustrated below with a different example here. For example, according to a poll conducted, the president has a 42% approval rating. Describe the sampling distribution of the sample proportion for samples of size 10, 50, and 100. So each one of these pictures, it's kind of hard to see, let me zoom in a little bit, is for sample sizes of 10, 50, and 100. So again, let's think of this as, let's say I'm conducting a poll, and I have 300 employees or people that are surveying for me. And on one day I tell them, okay, go up to 10 people. Each one of you go up to 10 people and ask them, do you approve of the president or not? Okay, some will say yes, some will say no. And if you look at this distribution here, very few of the surveyors actually had all 10 people that were in favor. You see how if it's 10 out of 10, that would be close. That would be a 1 proportion, right? There's also very few people that, when they went up to all 10 people, they were opposed, right? But for the most part, they had more of a mix, right? And if you were to look here, if I were to make a best guess at the center, I would say it's kind of hard to say, but I would say somewhere around that region, right? That seems like the most frequent proportion that showed up. Okay, so there's 300 different people that were surveying 10 people each. Okay. Again, now what about on the next day? I say, all right, same 300 employees that I have that are going to go out to survey people. Okay, this time I want you to spend a little bit more time and not just go up to 10 people, but go up to 50 people. Okay. Now, do you see that it would be likely that all 50 people will approve of the president if you're sampling randomly? Because again, all this is done randomly. Well, in fact, if you came up with this, it's really none of them, right? There's nothing that shows up as all 50 people. Okay, it's very unlikely. Okay. In fact, the only proportion that shows up, the highest proportion is that 60% of those 50 people were in favor of the president. Okay. And at the lowest, we didn't get all 50 people ever to say no, right? So we have nothing here for 0. The lowest proportion that we got was 0.2, it seems like. Okay. But again, most of these 300 samples came back with proportions somewhere around 0.4, around this region, because of the height of these histogram bars here. Okay, and then on the third day, you can see where this is leading to. Same 300 people. I say, all right, now I want you to spend even more time. Again, go out, and each one of you is going to survey 100 people. Okay. At that point, it's very, very unlikely that all 100 people that this one individual surveyor asked will all be opposed of the president. So you see very few, or actually none, are below, I would say, where's that? Like, that's like 0.3 right there. Very few are below 0.3. And then there's actually nothing beyond like 0.7, right, that are in favor of the president. But again, it does tend to still have the same center here, which is around 0.4 something. Okay. Now, what they're saying here is maybe a much larger poll, or previous poll suggested it was 42%, and it seems like that public opinion really hasn't changed since then. Okay, see how it's still kind of centered at 42%. So that's what we're trying to illustrate here. Again, when you are sampling a group of people, they are much more predictable than individuals, or larger groups are more predictable than smaller groups. All right, so the shape of this. Okay, as you start to see that as the sample size gets larger and larger, it does exhibit this bell shape, right? It starts to look more symmetrical. It's not perfectly bell-shaped, right? But it's approximately. So we say, as the size of the sample n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal, right? Or bell-shaped. What can we say about the center? Well, the mean of the sampling distribution of the sample proportion, that's p hat, equals the population proportion, p. So on average, all the sample proportions that you take should target the true population proportion. Okay. And then what can we say about the spread here? The standard deviation of the sampling distribution of the sample proportion, that's p hat, well, it decreases, right? It gets more narrow It becomes more narrow as the sample size n increases. All right, so the sampling distribution of p hat, well, the shape of the sampling distribution of p hat is approximately normal under certain conditions. And what are those conditions? Well, this condition is going to show up a lot in this course, and that is that np times 1 minus p is greater than 10. So it's not as simple as for the sampling distribution of a sample mean, where n just had to be greater than 30. Here it's a little bit more involved. Okay, there's an n, there's a p, and there's a 1 minus p. If that product, when you multiply those three numbers together, is greater than 10, then we can say that it's approximately normal. Okay. Now the mean of p hat, right? That's what that means. The mean of p hat does target the true population proportion. However, the standard deviation here of p hat is this weird thing here. Okay. Again, how they come up with this is beyond the scope of this course, but we know that the standard deviation of p hat does come out to be this. Okay, just like before, if we needed to come up with a z-score to look up the z-score on a table, then this would be the process. Again, z-scores are just whatever random value you're talking about minus the mean divided by the standard deviation. Okay, so in our case, the random variable that we're talking about is the sample proportion minus the mean of your sample proportion divided by the standard deviation of your sample proportion, which each part of this is, well, the mean of the sample proportion is the proportion, right? That comes from here. And the standard deviation of the sample proportion is this whole thing, this whole square root thing, which again comes from here. So if the distribution is approximately normal, and we are asked to find the probability of a proportion, we will need to find the area under the normal curve. And how do we find the area? Well, if you're using a table, you use a table. But in my class, we use a TI calculator. And of course, that function is normal CDF. Now let's go ahead and do an example here. Now I do want to start off by mentioning that all these questions are actually binomial questions if you look at them closely. Okay, which means that you can actually calculate them using the binomial CDF. But in this section, we are going to actually just use the normal approximation, if the conditions are met, of course. Okay, so according to the Census Bureau, the unemployment rate of the population in Orange County is 6%. Suppose we take a sample of size 200 individuals in the labor force from the population. What is the probability that less than 3.5% of the sample of 200 will be unemployed? Okay, so they're asking for the probability, right, that less than 3.5% of the sample of 200 would be unemployed. So they're really talking about some sort of proportion, right, when they're talking about 3.5. Now, if this was a binomial question, then, which it is, really, there's 200 trials. The probability of success is successfully identifying somebody that's unemployed is 6%. That would be like your P, and so forth. And then 3.5% of 200, well, that's 7. Okay, so you can think of this as what's the probability that less than 7 of the 200 are unemployed. So you can think of it as a binomial, but we're not going to think of it in that fashion because in this section we're seeing if we can apply this normal approximation. So what are the conditions to assume an approximate normal? Okay. Well, we need to know whether np times 1 minus p is greater than or equal to 10. Okay. And in this case, we need to know what your n is and what your proportion is. Okay, your n is your sample size. So we sampled 200 people. And the population proportion, the p right here, this is the p without the hat, is that 6% in theory are unemployed because, of course, this usually comes from a prior study or essentially a study of the population. In this case, this was the Census Bureau. So they already know that 6% of individuals are unemployed. Okay. Now, if we actually gather our own sample of 200 individuals, the question is, what's the probability that less than 3.5% of these 200 individuals are unemployed? Okay, so there's a chance of that, right? On average, it should be 6%, but there's a chance that it'll be less than 3.5%. Okay, so now that we know our N and our P, let's go ahead and insert those numbers here. We have 200, P is 0.06. 1 minus P, well, it's the complement, right? It should be 94%. So I'll just write it 1 minus 0.06. You can enter that in your calculator. I would make it a habit to be able to just come up with the complement in your head. 100 minus 6 is 94, so it's 0.94, right? Let's just run that through our calculator. Now, you're almost always gonna get this to be over 10, especially if the sample size is large enough. The only times you have issues is when your proportion is too close to 0 or too close to 1. Like in this case, we barely passed this test. We get 11.28, which is still greater than 10, so it meets the minimum requirements. Okay, so what does this tell me? This allows me to say that our sampling distribution of our sample proportion, because again, the proportion will change from sample to sample. It tells us that P hat is distributed as a normal. Now the mean of P hat, as we saw from the previous page, does target the true population proportion P, which they tell us is 6%. And the standard deviation of P hat is equal to that weird formula that we saw on the previous page, which is square root of P times 1 minus P over N. And we do have all the pieces to this, right? We have that square root of P, which is 0.06. We know that 1 minus P is 0.94, and it's all divided by N, which in our case is 200. And I do recommend you make that a habit to be able to come up with 1 minus P in your head, because I'm going to be putting that in the calculator, and you don't want to put in too many parentheses. And I'll show you how to put this in the calculator once we get to the question here. All right, so the main question here is that the probability that this sample proportion is less than 3.5%. Okay, so again, anytime we're dealing with probabilities for something that's normally distributed, we want to draw a normal distribution graph, which is a bell shape. Okay, the center here, well, the mean of our proportion is 0.06, and our standard deviation is this, right? So 0.06. And the question here is, what's the probability that it's less than 3.5? Well, 3.5 as a decimal is 0.035. This is 0.06. And 0.035 should be to the left of this, right? They're saying less than, so that means to the left. All right. How do you find areas underneath a normal distribution? Well, that is done using the normal CDF. So in symbol format, it's asking what's the probability that P hat is less than 0.035. Okay, and that's found using normal CDF because we know it's normal now. We have our lower bound, upper, mean, standard deviation. Now, in actuality, what do proportions range from? They go as low as 0 and as high as 1, right? There's no way they can be outside of that range. But for normal distributions, it goes from negative infinity to positive infinity. Now, another reason why we have to follow this rule here, this condition, is that if it doesn't follow that condition, then we would actually be able to find probabilities that this proportion is less than 0 or greater than 1. So again, that's one of the reasons that we have to follow that condition, because it should be impossible for a proportion to be less than 0 or greater than 1. Okay. But nonetheless, when you're coming up with the lower limit, we're still going to use negative infinity here, even though we know it can't be negative or less than 0, right? Upper, in this case, is 0.035. The mean here is 0.06. And the standard deviation is, well, that's the ugly part. Let me extend this here. Now, your calculator can handle this all in one shot. And I'll show you how to do that in your calculator. If you do square root, and you just do 0.06, and then I would multiply it times 0.94. That way you don't use too many parentheses, because you can actually close off the parentheses, and then everything you write after that won't be under the square root anymore. So you want to be careful with that. And then divide by 200 here. All right, let me show you how to put that in your calculator. Okay, so we're back at the calculator here. Let's go to second distribution and go to normal CDF. And our lower bound here will be negative E99. Just make sure you're using a negative symbol and not the subtraction symbol. Our upper bound here will be 0.035. I do expect this area to be less than 50%, right? Just by the looks of that shaded region. The mean here is 0.06. And the standard deviation here, let's go ahead and clear this out. All right, let's start off with the square root. And it opens up a parentheses. You want to do 0.06, and I would times by the complement of 0.06, which is 0.94. Again, this is another reason to be able to do that, because otherwise you would have to do parentheses 1 minus 0.06, close off the parentheses, and if you're not too comfortable with these calculators, you might close off the parentheses way too soon. Okay, and then just divide by 200. Okay, if you do it like that, you won't have any issues with excluding any of these numbers from the square root. So again, all these numbers should be underneath the square root. Let's go ahead and paste that over. And as you see, it does appear all under the square root. All right, let's go ahead and press enter here. And I get about 0.0683 if we're rounding to 4 decimal places. Okay, let's do another question. Now, there's another way that they could ask these questions, okay? Instead of them asking for, like in the previous question, what's the probability that that proportion is less than 3.5%, they might not give you a percentage. You might have to come up with it yourself. Okay, so like in this following question. It says, according to the Census Bureau, 10% of working population of Orange County carpooled on a car, truck, or van to get to work. Okay, so they're telling us that 10% is the true value, because according to the Census Bureau, right? Now, if we were to sample our own 150 people, so what's the probability that at most 20 of them carpool to work? Okay. Now, they didn't ask for a percentage, right? But in reality, they are kind of asking for a percentage. What's the probability that at most 20 of them carpool to work? What do they mean by 20? Well, 20 out of 150. So really, they are coming up with a percentage. 20 out of 150. Okay, so let's keep that in mind. All right, so let's see if we can apply this normal approximation. Normal approximation. All right, so what are the conditions for this? Well, again, we have to know if NP times 1 minus P is greater than or equal to 10. N is our sample size, and P is the true population proportion of what we're talking about. And in this case, we're talking about those who carpool. Okay, so our sample size was 150 individuals, and our population proportion here is 10%. All right, so let's go ahead and put that into this formula. 150 times 0.10. What's the complement of 10%? What's 90%? 0.9. All right, if we calculate that, what do we get? Well, again, we just barely passed this test. We get 13.5, which is greater than 10. So that's all that's necessary. Okay, what does this tell us? Well, it allows us to say that the sampling distribution of P hat is normal, is approximately normal. That means that P hat is normal with the mean of p hat being the population proportion, which in our case is 10%, 0.10, and the standard deviation of p hat is the square root of p times 1 minus p over n, right? Which is 0.10. We already know that 1 minus p is 0.90 over n. They say that that's, we took a sample of 150. Again, our calculator can handle that. I'm not too interested in what the decimal equivalent of that is, because I know our calculator can handle that, as we saw in the previous example. Okay, now this was asked a little bit different. They said, what's the probability that most 20 of them carpool to work? Okay, so they're not saying that p hat is greater than or equal to 20, because p hat can only range between 0 and 1, right? It's a proportion. It only goes from 0 to 1. So they're really asking, what's the probability that p hat is at most 20 out of 50? That's what they're asking. So they're saying, what's the probability that p hat is at most 20 out of 150? So can it be more than 20 out of 150? No, at most it can be 20 out of 150. So it has to be less than that. Okay, again, we are dealing with a normal distribution. P hat is normally distributed. So let's go ahead and create a normal distribution graph where the center is 10%. That's P. And 20 out of 150, well, I don't have a good reference for what that number is, so I'm actually just going to do that on the side here. What's 20 out of 150? Well, that is approximately 0.133, like about 13%. Okay, so where's that going to be? Well, that should be around, what's to the right of 10%, right? So this is 20 out of 150, which is approximately 0.133. Okay. Again, we are looking for what? The probability that it's less than this. So we are shading to the left. Okay. Just by the looks of it, I can already tell that this is going to be more than 50% because it's more than half of that normal distribution. Again, to find the area underneath a normal distribution, we're going to use normal CDF in our calculator. We have a lower bound, upper, mean, and standard deviation. Lower bound being negative infinity. I know technically proportions can't be less than 0, but we're just going to go ahead and put the negative E99 there just to be consistent. The upper bound is at 20 out of 150. I wouldn't put the decimal equivalent. I would just put 20 divided by 150. Again, your calculator can handle that. The mean here is 10%, so 0.10. Standard deviation, we're going to put it in like this, square root, 0.10. This is multiplication symbol, 0.90 divided by 150. Of course, that's all underneath the square root. Again, let's go ahead and show you how to do this on the calculator. All right, let's go ahead and click the second distribution, normal CDF. The lower bound is still negative E99. Upper, in this case, is 20 out of 150. So again, your calculator can just handle that, no problem. The mean here is 0.10. Standard deviation, let me clear this out. Square root, 0.10, you don't really need that 0, times 0.9 divided by 150. Close off that parentheses. Okay, and let's go ahead and paste that on. All right, let's go ahead and press OK. And just like expected, I did say that it was going to be more than 50%. It turns out to be a lot more, about 91%. So 0.9132.